first of all, I would like to explain a bit about the title, why there's this relation to the alchemy. Yes, because, I mean, alchemy, as everybody I think associates with medieval ages, right? With alchemists that try to transform lead to gold, yes, through processes they use. So that's this is a process of let's say transmutation, transforming. It's called transmutation, and there is also Japan. Because in Japan, also alchemists in Japan is Rekinjutsu. Rekinjutsu is the equivalent to alchemy in Japan, and the principle of transmutation, transformation is called Renzei. So to know Renzei in Japanese, right? So what is it about? It is about the taking material, the basic material. We are materia is we are all surrounded and we are out of materia. Materia is the material, right? We are off, right? We are and what alchemists do or did is to use special methods to transform the material. It's also about the state, the state of being. So you're kind of have gain knowledge about the world, about materia, about the universe, how everything is connected, right? Through methods, and what they did actually is how I understand it is they transform they use these methods and they perform these methods to mirror, to elevate themselves. So basically, to not go too far in this alchemy context is here. Let's see the object here, right? This is all the relevant positions, right? When you want to see an alphabet in this one shape. So basically, come back is all the alphabets in this model is broke down to one object, one object that is equivalent here to the alchemic process, the prima materia. Prima materia, the shape, right, that can become everything. So, right. So that's the inspiration I had. That's why I connected it to the title, to the alchemy, right? It's like a unfinished cube. So, no, there are parts missing, but basically it's a cube. It's a very simple phenomena about it is when you add the movement, the rotation, and know how to move it, you will see the letters, right? As I can successfully, more or less, there are some letters there. Of course, when you would watch it look at it without knowing it, without knowing the context, we would probably not decrypt it. But if you see the whole context, it works pretty well. So yeah. So in this one object, we have elements. These elements of okay. There's a notation. I will come to the notation term later. What is notation and all? So it is a notation. The method, yes, the method is the algorithm. So I understand it like that. You have the object itself, but it bring you nowhere, or you don't know nothing about it when you don't know the algorithm. The algorithm is how to move it, right, and the exact positions and that. No, this is we can say here. Okay, maybe because I'm a B. I don't know how you see it, but C. C. So it's a notation because it's the alphabet from A to Z. So let's see some examples of notations. So what is notation at all? The notation is record system that humans invented to communicate, to break things down, to describe phenomena, to share it, right? So alphabet, for example, is we operate all alphabet with the language and the alphabet. In alphabet, the alphanumerical code is a code, but also a notation, right? So what is the code and notation? Code language. The code can be everything. Language. For example, they have their own codes. There is codes that, for example, giraffes communicate with that we cannot hear. It's because it's a very low frequency, but it's a code. So basically, we're surrounded by codes, and we try to decode the world. And but notation is a form to write or to record visually on surfaces. So since ancient times we note on surfaces, like when you see the Egyptians or so they in every culture, but notations are also for the music. That's a very famous notation, and that's the difference. The clear difference between notations is that notations are records. We write or we have signs that are on paper or programming language. Programming language. Say code, because code that's the most used for for the word code. That so we immediately associate code with coding, computer coding. But so to explain it, the programming language that contains the signs is a notation, and that's a notation. So we so it's a language between machines and humans. So because the machine, for instance, it doesn't work with programming language, like, right? It can translate, so it understands the language and translates it for to the machine language. Yeah? It's like a bit. It's good. Machine language is a very long numbers of ones and zeros. So we humans, we're not capable of the machine language. We're capable of the language, programming language that is to interact with the machines, but the machines don't operate with the programming language. Okay, so but there's also a notation is, for example, a notation of a let's see that here. So this is it's a representation, represents an object in space, right? Like a spatial object is represented by this notation that we all know, because we learned about the perspective, so we can read that, and we are linked to the spatial object. But it's a symbol, right? It's a symbol of it, and actually a spatial object is a time and space phenomena. So it's never it's always in movement. We never perceive it. It's like not a fixed form. It's always in movement. It's an event, actually. So all objects are events, we can say. No, everything is surrounded by our events, and then we are extracting them and putting in notation. So, and there's many representations of representation methods of space, right? So this is the perspectival method that arises in the Renaissance, right? This is like the perspective that there is a one point when just the lines will run into, or and then yeah, and this was always the representation was always somehow a problem for the artist as well, no? Because in art history you see they're all struggling. How can I put space, the space phenomena in a picture, for example, no? Because you have always in one picture. So since until the Renaissance, there were this. Okay, this is you could just represent, but you never could put a time space line. So the situation, for example, the perspectives, because everything is like moving, no, and transforming in the real life. How can you put it? Or they really struggled to to put it to find a representation method of reality. So you can see. For example, I have here the Cubism, yeah, Picasso, for example. It's very, yeah. So everybody knows Picasso. When you see this picture here, so to decode it, yeah. So it's not a naturalistic record of the woman. Is more there's more perspective in it, like the whole movement. So so Cubism tries to break through the perspective, the common Renaissance perspective, and tries to find new ways, no, here to like film. Nowadays, or film is longer, but this is step further, that you could that you could put the space-time in one format, right? But it's not even because film is yeah, it's also the two-dimensional linear frames. So there's a problem to how to put movement and the situation into to represent it, to make a notation. And yeah, and I show you another. I hope you can follow, because I'm a bit fast. And here, for example, this is David Hockney. This is a Polaroid series. So each one here picture is a Polaroid, and put it together to one plate, time-space plate, right? So that is describing the situation somehow. Yeah, there's much more information. So because you don't need in this case one picture how this man looks like. Here you can see his movements, and the space is, yeah, it's autosymmetry. So this is like more similar, better representation of our reality, right? Because that's like that. There is no one fixed perspective picture. Okay, so yeah, that's another point. Another notation by David Hockney, out of oops. And good. And there are like all the representations of object in space. Parallel projection is an isometry that you know it from many different examples you've seen, no? Like this is the isometry. Here, this is the grid, so you can construct objects, but they are, yeah, it's symbolic, but it's very informative, right? You can and it's graphic. It's let's say attractive in a aesthetical sense. You can make a lot, and illusionists, for example, work a lot with isometric representation. But you see also those things in Japan, old Japan, in those here paintings around 17th century. So they are using this kind of, or here, for example, this is also, you can see that this is this isometric representation, and yeah, some newer like from Acrobat, from Adobe. You know, those things are very common. Like, so you can build these things endless. And Escher is also in this context very interesting here. MC Escher, no, the impossible pictures somehow. No, this is the total impossible, but you can trick with notation. You can trick because it's not reality. It's like the representation in the ISO grid, so ISO grid. So the lines they don't come together. This is always parallel. No? And so, but I can show you here how it actually is. So super simple. In the program we're gonna learn, or we will work with. I proposed. That's the SketchUp program here. I hope everyone has access to it also. So, but yeah, that later to the practical here. This is the Escher's waterfall that is impossible, no? And you can see camera. This is, I have the German version, but you can we'll figure out. Perspective. This is the non-perspective, but it just doesn't work with this representation perspective. The real perspective we know, no? It just this is this is the whole secret of it, right? This is a 3D model of this waterfall, and it will never work because this perspectival view is just not possible, mathematically not solved. So that's why isometric projection, and then you can assemble it to that. Right? This is how we work. But he was working. That is very interesting without computers. So now today we can reach those, come to those results much faster and understand it much better when we use tools like this program. So I would like to share this program because this is what shaped me a lot, right? This is this how I learned spatial thinking, or this inspired me a lot. And then at some point, yeah, also the object here, the ABC object arise also from SketchUp. So I was working a lot with SketchUp. So okay, then I'll show some more. Okay, notations, right? Some examples. So, yeah, the principle. For example, here there is a colleague of mine. He built recently like a monument here in Berlin that is in front of the School for Performative Art. Yeah, this is a big monument, and it is about actually what we will what this workshop will be aiming. So how objects change their shape according to to your point of view, to the perspective, right? So this is basically like a graphic logo, of a house here. This is like a very simple representation of the house, and but it's only readable from as such only from one perspective. When you just stand in one place, then you can read it. Otherwise, it's changes the shape. So I will. This is a model of it, right? You can see a model. How good. It is. Yeah, somehow. So you can see the house. I don't know. Can you see it? Or is it here? So and it's yeah, and it's like transforming. Depends where you stand. It's like a model, but in the space, in the urban environment, you have to be in to decode it. No, there's like a spatial code, you can say. I would like to also make it understand better what is a notation and how relative the perspective. The things are depending of the point of view of the perspective. So there is very interesting video work from Ray and Charles Eames. You know Ray and Charles Eames. This is yeah, the designers, American designers. I mean those chairs, for example. This. You know that chair. This is Charles Eames. They had. They're quite revolutionary. They had this architectural lab in LA, and they were experimenting a lot. This is they are the inventors of these shapes. Actually, back in the days, it was not possible to produce those shapes. More shapes. Okay, but I will show you the video first.
The picnic Near the lakeside in Chicago is the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now, every 10 seconds, we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds. The day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1,000,000 meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the sun. Followed by the massive outer planets, swinging wide in their big orbits. That on orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. 10 to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last, we pass the bright star Arcturus and some stars of the Dipper. Normal, but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan. 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance of the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of a sleeping man at the picnic. 10 to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn, an outer layer of cells, felty collagen. A capillary containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus, so massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. Proton filled our scene, reached the edge. Are these some quarks in intense interaction? Our PJAIT taken us to 40 powers 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
Yeah, so that was around 70s, no, in the 70s. So it's a notation, and it's interesting when you imagine that basically now the situation or looks like it. So this is total like real, no, and that was. Yeah, it's important to me to show that, you know, and this was it's actually a linear, somehow a linear notation, because it's you can say it goes in a line, 3D line, so it's like you just follow the axe away, and then again close. So, but it's like a linear notation. Yeah, this is like kinetics sculpture. That is from one. Yeah, it's kinetic because it's turning all the time, you know, slowly, and it can look. Depends from the point of view as a circle, or as a square, circle and a square. So this is, and this is, those are the between states of it. So there's movement included in that. So basically, and then I show you there was just quick review. There was a big exhibition in Berlin in the Academy of Arts in 2008, I think. Yeah, it was about, the whole exhibition was about notation. What is it's also art in arts, no? And I think there were like more than hundreds of works, and it's all about notation. So there are several examples. Can you just see quick through it? Yeah, this is the same phenomena here. Non-notation of an object, an apple, and then it depends how you move, where you are in space. And so the complete reality changes because you depends on the point of view and the position in space. Here, this is like a bit tricky. It's a three-dimensional wire object. And this is only a photo, so but you can imagine when that turns or you walk around, how many shapes you get. Like this is infinite. No? Here is a notation. So it's another. But those are like two-dimensional notations on paper. Here. And they all have function. There's a function behind it. It's a noted code that represents something, right? Some functions. Or here, for example, right? Yes. How? It's more time and space, representation of time and space, and phenomenon. So yeah, so there's a lot more than alphabet, right? To represent. Yeah. Okay. Here, for example, a good example of what is code and what is notation. I mean, I think it's now maybe more understandable, but here you have, for example, notation. So this is the notation for in Zen monasteries in Japan. There is this. They have the code, the Han. Han is like a wooden block on the hammer, and they have when they meet to meditate, then they hit with a hammer on the block, on the wooden block, and this is like a certain code. And then the master, for example, can see, okay, how good the student is, how far he's in his meditation, depending on how fluid and good he hits the wood. So okay, but just to know, this is the notation for it, and here you have a a moment. Here this is the code. Just so the rhythm itself is a code, and this is the notation of the code. So I'll show you that just to so and so on, no? So, but that was to show the difference. This is the code. The hitting is the code, and this is the notation of the code. So okay, but I think it's clear now. Okay, pretty much. So maybe on this. So Richard Winiarski is a very important picture. He also notations. It's a conceptual Polish artist from the 60s. But what is very important this picture in this picture, because it's around like 73, and this is the picture. So he was painting like that. So this is like the painting. 1 meter on 1 meter by 1 meter, and it, for me it seems visionary also, because first of all this is like a QR code, right? So QR code 73. I mean, it was not totally not existing, and then he includes this space, so he leaves the spatial notation. So it's a very important artist, Polish artist, actually, in this context, in the context of digital, how the digitalization arises. Right? The pictures were before.